This is a mini lecture on analyzing a more complex series parallel circuit. And I got this from a different book, so I'm just going to put the schematic onto the circuit here. There's a 9-volt battery with an internal resistance of 0.5 ohms. I'm going to hook an ammeter right next to that. And then I'm going to put a piece of wire. And then I'm trying to grab this resistor. There you go. And of course I could have all prepared this already, but I figured I might as well record that here so that you perhaps entice you to use this construction kit at Physics Educational Technologies as well. Because of course, as you can see, it is kind of fun to play with. Okay, I'm thinking that I might run out of space here. Let's see. And then of course I still have to change all of these. Not done yet. Oh, I do have a complete circuit. Okay, maybe not as pretty as in a book. Okay, last resistor here and a couple more wires. There we go. And at this point, don't pay attention to the measured electric current because I need to change all the resistors according to this schematic that I got from a different physics book. So you can see what I put in here. Okay, and actually if I click on show values here, oh, there we go. Much nicer. Well, almost an overkill, but at least that way we can see what we got. These two down here are 5 each. Well, that's a little weird. I don't remember clicking this here to leave the value out. I'm going to pause this here for a moment. Okay, I don't know why I turned the values off. Anyway, let me just check against the schematic that I have in front of me. That I got all the values here correctly. Okay, so here we have a number of resistors that are in parallel and or series, and we have to figure out what the equivalent or total resistance is. We can already figure it out because I put an ammeter in here. So all I have to do is 9 volts divided by 0.89 amps, and that of course comes out to 10.1 ohms, or perhaps around it 10 ohms. So keep that in mind. When we're done with this, we should come up with 10 ohms, because according to Ohm's law, it's 9 volts divided by 0.89 amps, which is 10.1 ohms. Okay, let's analyze what's going on here. These two resistors are 5 ohm resistors. They're in series. These two are in series, and then these two are in parallel with this. This one here, the 6 ohm, is in series with these three, and then this whole thing here is in parallel with these down here. Okay. Then these two are actually in parallel with each other, and then finally all of this here is in series with these two, and with this one, and with this one. So what I'm going to do now is I'm going to follow what they've shown you in the book on how to analyze the circuit, combining series and parallel parts, until I'm just going to be left with one equivalent resistance, which should come out to 10.1 or 10 ohms. Okay, I'm going to start with these two 5s here. So if I take one of these out, let me see if I can do that. Remove. There we go. And now I'm going to change this one to 10 ohms, because these two are in series, so 5 plus 5 of course is 10. And notice when I do that, I'm back to 0.89 amps. Okay. These two here, 4 plus 4 of course is 8. So I'm going to take one of them out. And I change this one to 8. And then I guess I just figured out that automatically it takes off the value, but there it is. So 4 plus 4 equals 8. The circuit, you see these electrons here flowing. Well, they are flowing because it's actually a complete circuit, as you can see. And this one here is just kind of hanging freely, not participating at this point now, but of course I'm going to put it back in. And there it is, 0.89 amps. Okay, these two are in parallel. So what I'm going to do on the side is I'm going to do 1 over 8 plus 1 over 4 equals 0.375, which I invert again, and I come up with 2.666, and so on. So I'm going to take this one out, and this one I'm going to change to 2.67. There we go. Show value. There we go. And then I actually don't need these two wires anymore, so I don't know why there's a junction. Odd. So these two that were in parallel here, 8 and 4, in parallel comes out to 2.67 ohms. And as you had noticed before, when you have resistors in parallel, the equivalent resistance is always smaller than the smallest one. Okay, now these two are in series with each other, so that's a combined 8.67. Okay, and the current is still 0.89 amps. These two are in parallel, and you can see here that junction is the same as this junction, so yeah, the current is going in here. In fact, I could take this off. Let me do that. I'm going to split the junction here, and I'm going to remove this one, put this there, put that there, and notice nothing has changed. So the current coming in here is also flowing out here. Alright, so 8.67 and 10 are in parallel. So I'm going to do 1 over 8.6666 plus 1 over 10. That gives me 0.2153. I invert that, and I come up with 4.64 for these two here combined. So I'm going to take one of them out, and the other one I'm going to change to 4.64. and you see the current is still at 0.89 amps. Okay, these two are obviously in parallel, so 20 and 5. That is 1 over 20 plus 1 over 5 is 0.25. I invert that and I come up with 4 ohms. And again, my total current is 0.89 amps. Okay, and now all the remaining ones are in series. So I have the one at the bottom, the 4.642857, I still have that on my calculator, plus, oh, turn the value back on, 4 plus 1 plus 0.5, and I come up with 10.14. So if I remove this one, this one, and this one, and change the one remaining resistor to 10.14 ohms, and there we go, 0.89 amps, and the total resistance is 10.14 ohms. And that's an example on how to analyze a more complex series parallel combination circuit.